Okay, it has been great to be here, very stimulating week. So my talk is about magnetic skyrmions, mostly about their quantum and their non-equilibrium dynamics. I'm also in between changing places, literally. So last week I was at the University of Basel, and next week I'm going to University of Cologne. So I'm in this phase, but the work I'm going to present now has been done in Basel. So in the group of Daniel Lowe, so in collaboration with Silas, Pavel, and Yelena. I'm pretty sure most of you are familiar with the concept of magnetic skyrmions. So these are stable, smooth configuration of magnetization, where the spin in the center of this texture in the ferromagnetic background, it points in opposite directions. And quite formally, they are characterized by a mapping where you go from real space to spin space, and this mapping is characterized by a finite topological charge given by this formula, where here M stands for the magnetization field. Magnetic skyrmions have been already predicted theoretically in mid-90s, but it was their first experimental observation in 2001 that boosted a lot of interest, and since their realization in bulk magnetic magnets, it has been observed in multiferric insulators and ultra-thin metal films. Originally, it has been observed in a skyrmion lattice phase, so that means that skyrmions interact with each other and they can condense in an ordered phase. And typically, they are observed in this phase diagram. Here it's the out-of-plane magnetic field, and here is the temperature. And these original skyrmions are very big objects, so they range between 50 to 100 nanometers. Nevertheless, more recently, it's possible to observe atomic scale skyrmions with a lattice spacing of 1 nanometer, and that inspires works towards the quantum properties of these particles. Of course, skyrmions do not exist only in crystal lattices. Individual skyrmions can be created. So for example, here, by locally ejecting electrons from a spin-polarized STM tip, the authors demonstrated that you can, in a controllable way, you can write and delete individual skyrmions, or in this experiment, by exploiting some instabilities coming from the edge of the magnetic material, these domain walls can be transformed into skyrmions by a specific magnetic field protocol. Okay, now for what happens in the more recent years, there is a lot of effort to be able to stabilize skyrmions at room temperature. And this is achieved, for example, in multi-layers, where by varying the ferromagnetic layer, it is possible to control the magnetic interactions and therefore to control the thermodynamic stability, or even explore some more metastable phases where the equilibrium skyrmion lattice, which is stable only in a very small parameter of magnetic fields and temperature, can be realized in a more extended parameter region by some protocols of field cooling. Of course, the goal is possible applications. Skyrmions appear to be very good candidates for these ideas of racetrack memories, where information is encoded in individual skyrmions, and then by, for example, electrically moving them around, you can read and write information. Nevertheless, besides applications, skyrmions are related to a lot of interesting physics. For example, towards the direction of topological quantum computation, where it has been demonstrated that if you have a skyrmion on top of an S-wave superconductor, then a Majorana zero-energy bound state can be realized, or the skyrmion Hall effect. So this is an effect related to the topological charge of the particle, where it has been observed these curved trajectories in a direction perpendicular to the direction of the applied current, or even topological magnons, so topologically protected chiral edge states around a skyrmion lattice that Sebastian is going to talk about soon. One of the key properties is their high mobility. So it's well known that they can be manipulated by currents several orders of magnitude less than the ones required for a domain wall. And they can reach very high velocities of around 100 meters per second. And that is in a metal. In an insulator, there are several proposals how to manipulate skyrmions, for example, with magnon currents, as you can see here, using thermal gradients, magnetic field gradients, or even microwave fields. Now, how about the theoretical prediction of these particles? Usually, any magnetization texture can be described theoretically by this Landau-Lifshitz-Gilbert equation, where it's more or less the classical equations of motion, with an additional phenomenological term introduced by Gilbert that accounts for damping mechanisms that are present in the system. Instead of having this equation, we can simplify a bit the dynamics if we consider we have a rigid body. So let's say the Skyrmion is described by one collective coordinate, the center of mass. And then we can arrive at this equation, which is a particle-like equation. It's known as TLS equation, and the first term is the Magnus force. So it's an out-of-plane force which is proportional to the topological charge. And here we have some damping mechanism. And these damping mechanisms are velocity dependent and describe how the Skyrmion interacts with other degrees of freedom. That could be either electrons, magnons, or phonons. But we don't have the microscopic details of this dissipation mechanism. It's just phenomenological. Of course, this is an equation only for an insulator. In a metal, in the presence of currents, we should add additional spin torque terms. So what is quantum about Skyrmions? So that is the goal of my work, to try to go beyond the classical framework and address the quantum dynamics of these particles, and try also to derive the microscopic origin of dissipation in an insulator. So we consider the following system. We have a number of two-dimensional layers, and each layer hosts a Skyrmion. And if we want to address the quantum dynamics, we have to employ path integral methods in imaginary time. And I will go very briefly over these methods. So to describe our model, instead of using the magnetization field, we introduce this spherical parameterization. So we have fields theta and phi, and we write the Euclidean action of the model. So here is this Vesumino term, is the term that describes the dynamics, and we have this energy functional. So the idea is that we have to write the partition function as a path integral over all possible realizations. And we want to employ a method that separates the center of mass, which is the only relevant dynamical coordinate, from the other degrees of freedom. So we promote the center of mass to a dynamical variable. Here m0 is the static Skyrmion, and we also consider fluctuations around it. So using methods from quantum field theory, then we arrive in a partition function only for this collective coordinate that contains information we already know at the classical level, for example, the presence of potential, the Magnus force, or external forces, but also contains a new dissipative term that describes the interaction of the Skyrmion to the magnetic excitations, and that will give some dissipation. As a particular example that we are going to use our results is this energy functional. So here we have the exchange interaction, the DMI interaction that is responsible for the interesting physics of Skyrmions, some anisotropy and magnetic field. Now, if we minimize the energy functional, we can parameterize the Skyrmion. For example, find what is this field phi and theta. And theta describes the Skyrmion profile, so how the spins rotate from the center out. And here lambda, it's an important parameter, is the Skyrmion size. This energy functional supports many interesting phases depending on the parameters. So we can have a cone, a helicoid, or a Skyrmion lattice as a ground state. But we focus on this region where isolated Skyrmions exist above the ferromagnetic background. I should point out that our theory and our results are quite general, so we could generalize and put another type of DMI interaction, for example, the one that stabilizes anti-Skyrmions, but that's not what I'm going to talk about. But it's quite general, our derivation. Now, on top of the Skyrmion, we need to calculate the magnetic excitations, the magnons. The magnons appear as solutions of an eigenvalue problem. And of course, we have these non-localized states, the scattering states, that exist above a gap, the magnon continuum. And the gap is given by the anisotropy and the magnetic field. But on top of that, below the gap, there could exist some localized bound states that correspond to different deformations of the Skyrmions. For example, the breathing mode and some distortions. And depending on the parameters, there are several studies that have demonstrated that you could always have a few of these localized bound states below the gap. Okay, so in a work that has been summarized in this publication, we are able to generalize these micromagnetic equations of motion for the case of an insulator, and we demonstrate that the dissipation coming from magnons is in principle non-local, so it's non-Markovian, has memory defects, memory effects, and these memory effects, of course, are linked to the underlying microscopic details. Nevertheless, these memory effects can be negligible, and to find the time scale, we can go to frequency space, so Matsubara space for us, and see what happens for very long times. Therefore, for very small frequencies below the gap, the leading contribution that comes from dissipation is a term that is omega squared. That means we have an effective mass. So the leading contributions of magnons give rise to an effective mass, contrary to the description before, where we would expect that coupling your particle to a reservoir will give you friction. Okay, so since I promised our derivation is microscopic, that means that I can calculate this mass in a closed form. So indeed, we find a semi-classical mass. I say semi-classical because it scales with the effective spin. So Na here are the number of layers, and S is the effective spin. Here I take a sum over all magnon modes. Epsilon is the energy of the magnon modes. But it turns out that these matrix elements are zero when I have translational symmetry. So a skyrmion that moves in a translationally symmetric space behaves as a massless particle. In order to generate a mass, we can consider some spatial confinement. For example, we can consider a magnetic trap that is realized by putting an out-of-plane magnetic field. So here we have the skyrmion, and this black line here corresponds to the magnetic trap. And I can calculate now what is the mass in this case as a function of the size of the trap. So the mass is going to increase, reaches a peak around the skyrmion size, and then is going to vanish when translational symmetry is restored. Another interesting limit is the case where I have quasi-one-dimensional confinement, where again the skyrmion is going to behave as a massive particle owing to its confinement. And of course, this is relevant to the technologically important case of a racetrack. So that is the semi-classical mass, but on top of that, we calculate some quantum corrections. So this is quantum because it does not scale with the effective spin, but has an explicit temperature dependence. So here β is the inverse temperature. And of course, here it's plotted as a function of the temperature, and you see it grows. But the interesting thing is that at low temperatures, which is best visualized here, it remains finite, right? So this reflects the fact that these are contributions from the quantum fluctuations that do not freeze out even at very small temperatures. So we have an effect, explicit effect given from the quantum fluctuations. This kind of dynamics could be relevant for the atomic scale skyrmions, so very small skyrmions, where quantum fluctuations are expected to be important. Okay, so now you might wonder what are the physical observables of having a mass. So this has been explored in this experiment where the authors used a magnetic bubble. It's a bigger particle. It's stabilized by long-range dipolar interactions. And they placed it in a circular disk, and they argued that the trajectory of the bubble, if the particle is massive, can be explained by two distinct modes. So by measuring the trajectory of the particle, they can infer a lower bound for the mass, which is rather big for a magnetic particle. Now I should point out that according to our formalism, the inertia mass is associated to deformations. So if we have some bound states, they will contribute more to the inertia mass. And this is supported by the experiment where this large value has been attributed to the excitation of this breathing mode by the confinement. Of course, we should be very careful and think that our results apply only to insulators, and there exists an example where magnetic skyrmions have been observed in an insulator. So in the case of a confinement, we expect a mass of 45,000 electron masses, whereas the quantum mass at low temperature is at least 2 orders of magnitude smaller. Okay, so that gave us the idea to proceed with studying quantum phenomena, and of course the most interesting one that describes the interplay between classical and quantum mechanics is quantum tunneling. So imagine we have a skyrmion that is pinned by a potential, and this potential, for example, exists naturally from defects. And of course, deepening can occur thermally, so at enough temperature, the skyrmion can tunnel as the classical mechanics dictates. Nevertheless, there's always the possibility of quantum tunneling. So the skyrmion can tunnel to the classically forbidden region, and this behavior has been already experimentally verified in a series of macroscopic objects, for example, a domain wall, a vortex in a superconductor, and Ricardo has a lot of work on magnetic vortices along this direction. So for the case of a skyrmion, imagine we have a potential of this form, and the skyrmion is pinned down here. The Euclidean action for the model that we need to employ in order to calculate these transition amplitudes, of course, contains the Magnus force, the mass, and this potential, where we have the pinning potential, and we also take into account an external force that is going to tilt a bit the potential and minimize the barrier of the height of the barrier. Now we note that to observe quantum mechanical behavior, the barrier has to be narrow and small, which is mathematically written in this way. So here Fc is the critical force we need to apply in order to vanish the height of the barrier. So since we are in this region to observe quantum mechanical behavior, that means that the mass is going to be very small. Therefore, the skyrmion is going to perform a trajectory which has a component with a fast cyclotron motion superimposed to this slow guiding center. So that motivates us to ignore the inertia effects. So there is a way where we can go from this Euclidean action to this one, where we integrate out the fast motion and simplify a bit the dynamics. Okay, then we note that to study the tunneling effects, only the trajectories that minimize the action are going to contribute. So these are the instanton trajectories, and they are the solution of the classical equations of motion at imaginary time. And to find that in our particular problem, we have to satisfy this condition. Okay, so the potential has to vanish. And here we plot the equipotential lines of the potential. So the instanton trajectory is given by this black line. So the skyrmion starts at the center of the potential and then tunnels out at this distance, which is the turning point. And okay, we can calculate microscopically all relevant components for the tunneling. For example, the tunnel frequency, which is small oscillations at the bottom of the potential, or the WKB exponent. And it's important to note that here depends only on A, which is the width of the potential, and it does not depend on the depth of the potential. Now, to observe such phenomena, two conditions must be satisfied. The inverse decay rate has to be within some hours, so we don't have to wait infinite amount of time for tunneling to happen. And also the crossover temperature, when the thermal activation happens, should not be very small, should be detectable. And okay, let me take you through this table, which is just a calculation for this magnetic insulator. And here we have the size of the skyrmion, so very small skyrmions carrying some thousands of spins are going to tunnel this distance in this amount of time in the millikelvin regime. So by properly going close to the condition for observing quantum mechanical behavior, it is possible to observe it for this topological particle. Okay, so now I would like to talk about more on some non-equilibrium effects that we could observe. And the idea is as follows. So throughout our derivation, we start from this magnetization field, and we break it into a central system, the skyrmion, and it's coupled to the magnon bath. And we ask the following question. What is going to happen if we turn on some time-dependent magnetic field? So we know that if we have, for example, a gradient, it's going to couple directly to the central system, so it's going to give us a force. Nevertheless, unavoidably, it's going to couple to the Magnon reservoir. So we have a drive that couples in the Magnon reservoir, and these kind of processes are usually neglected. And then we note that the Magnon bath is going to couple back to the central system. So I'm going to demonstrate a situation where this could have some measurable consequences. Okay, so imagine we put the skyrmion at the center of the nanowire, and at some initial time, we turn on a magnetic field gradient. Since it's a gradient, that means it will exert a force, a linear force on the skyrmion. Here we have the Magnus force, here we have the dissipation kernel, and we take into account some confining potential coming from the edge of the nanowire. So what is new here? First of all, this derivation is in real time now. So what is new is that this dissipation kernel has a contribution of the equilibrium situation, like coming from the confinement, but also has additional contributions coming from the external drive, right? So our Magnon reservoir is driven. So if I want to study a bit what happens, so this is the kernel, the dissipation kernel, at a given time. So if I have no external field, it's the blue line. So for very small frequencies, like we did before, I have frequency squared, and that means a mass. But once we turn on the external field, new terms emerge which are linear. So we have a super-ohmic to ohmic transition. So we have new ohmic terms that appear here. And these ohmic terms come from the external drive, right? But of course, these are all periodic in time. So if we want to neglect, again, memory effects and do the same thing like before, but the situation now it's a bit more complicated. So we will arrive in this very ugly equation. But the terms are rather simple because we neglect, again, memory effects. Nevertheless, these new terms have inherited the periodicity of the drive. So in the end, we have a time-dependent dissipation that originates from the periodicity of the drive. And let's see what are the physical consequences. First of all, we fixed to be on resonance with the breathing mode, which is very relevant mode for out-of-plane magnetic fields. So if we neglect this new type of dissipation and we just keep the mass and the topological charge, the skyrmion is going to start from the center of the nanowire. It's going to reach this point where the force changes sign, and then it's going to go back. So over time, nothing interesting is going to happen. The skyrmion is going to move around this bounded periodic motion. But that's not quite true, because we know that the drive is going to change the way the skyrmion dissipates. So in the end, the skyrmion is displaced, and the displacement is visualized here by this coloring, and the arrow shows the direction of motion. So the skyrmion is displaced along the long axis of the nanowire, and I should again point out that there is no force that is really pushing the skyrmion in this direction. It's just that in half of the cycle, the skyrmion behaves roughly like a massive particle, and in the other half, it behaves as a diffusive particle. So it will never go back to its equilibrium position, right? So this is just one demonstration where we can influence the dynamics of the skyrmion and the way it dissipates. An interesting quantity to visualize that, we can just take the average of the position over consecutive periods, and it's plotted here in the blue line. So over time, the skyrmion is displaced. So like to put it in real values, so within 70 nanoseconds, the skyrmion is displaced around 6 nanometers. Okay, so let's see a phenomenon that kind of combines both this non-equilibrium dynamics and the quantum dynamics. What I have talked so far, we have a skyrmion that is coupled to the Magnon reservoir, and that will give rise to a mass. And then I talked about the case where I have a skyrmion coupled to a Magnon reservoir, which is externally driven, and then will give rise to, let's call it, driven dissipation. So a dissipation that inherits the drive. But it's not quite the full story, because we know that at any finite temperature, there is thermal noise that renders the propagation of the skyrmion stochastic. And in principle, both this noise and this dissipation kernel are defined by the way the skyrmion interacts with the reservoir. And this is the well-known fluctuation dissipation theorem. This is a very standard theorem for mesoscopic systems. So here we have the correlation function for the random force. And this correlation function is related to the dissipation function. And we give it in the quantum mechanical version. And we ask the following question. Is it possible to restore similar equations and similar relations for this non-equilibrium driven case? So it turns out that we explicitly find by calculating within first order perturbation theory that both the dissipation and the changes in the fluctuation can be decomposed into this function. So a function that depends on the Magnon reservoir multiplied by a function that depends on the external drive. Then we can relate those two functions and find this non-equilibrium fluctuation relation that kind of resembles the structure of the equilibrium one. And I should also point out that here, although we did it for a periodic drive, here it's quite general. So you can have any type of time-dependent drive as long as its amplitude is small. Okay, this is really not new. The Brownian motion for a skyrmion has already been observed. However, the typical assumption is that it's a white noise. So the different components of the noise are not correlated. And it also scales with this phenomenological Gilbert damping. So for example, having this assumption, then one could make a very specific prediction. For example, the mean square displacement is going to scale linearly with temperature, right? This is very trivial. And the way it scales linearly with the temperature is because this autocorrelation function scales linearly here with the temperature. Okay, so that motivates us to see what happens in our case. So I should remind you we have a linear dependence coming from this term, but also our quantum kernel has some temperature dependence, right? So in principle, we should have temperature dependent square. So this is a very specific prediction we make that for a magnetic system, an insulator at very low temperatures, the mean square displacement should scale quadratically with temperature and has a faster thermal activation. And there is another observation on top of that. Now we look at the root mean square displacement. So here goes linearly, but at very low temperatures, of course, as we expect, is going to stay finite. So even at low temperature, 0 temperature, the skyrmion has a finite root mean square displacement as a result of the quantum fluctuations. And let's say this value, if we plot it as a function of the size of the skyrmion, we see, of course, that the quantum fluctuations are important only for very small skyrmions. Okay, so to summarize, we addressed through our work the dynamics of magnetic skyrmions. So first, we studied the quantum dynamics, and we found that a skyrmion in a confined geometry behaves as a massive particle, but also the quantum fluctuations are important that will give rise to some mass at 0 temperature. We also studied the problem of quantum deepening and showed that in the millikelvin regime, it's possible to observe such phenomena. We addressed the non-equilibrium dynamics and see what happens if a drive couples to our reservoir and what are the physical consequences for such a phenomenon. And we also addressed the stochastic dynamics and talked about some non-equilibrium fluctuation relations and some novel predictions for the mean square displacement. So thank you for your attention, and I'd love to answer your questions.